everybody, and welcome to the online certification course by NPTEL on semiconductor devices for next generation field effect transistors, physics perspective. Lecture topic is Introduction to MOSFETs. We had looked MOS as a two-terminal device, and the various characteristics of a two-terminal MOS device was explained to you, and its operation under gate bias was only explained to you. This is for the first time within this course when we will be taking MOS device, and we will be looking into, first of all, we will introduce to you MOSFETs. Those who are not initiated in this domain can look into my other NPTEL lectures also, but this gives you a brief overview of MOSFET. In subsequent classes, we will take up your IV characteristics of MOSFET. IV means here current versus voltage characteristics, which means that if I vary the gate voltage and the drain voltage, how does the terminal current of a MOSFET vary, right? That is what we will be doing in class number 2. In class 3, which is the next class, we will be looking into a much more mathematical modeling of capacitance for MOSFETs at both high and low frequency. In fact, if you remember in our previous lectures, we have understood how the capacitance will behave at high and low frequency of the input signal. So, if you vary your input signals and want to find out the capacitance, what are the mathematical tools available and what are the analytical expressions which you will encounter while you are discussing a capacitance modeling. We will be specifically looking into high frequency modeling of MOSFETs, and the reason being that all these devices are primarily used for should be used for high frequency applications, right, where the speed of the circuit is pretty high. So, we should know how does a MOSFET behave at high frequency, and that is the reason class 4 is being shown to you. And finally, in class number 5, which is the last class of this week, we will look into the MOSFET as a switch and as an amplifier. So, as a switch primarily meaning as a switch all of you are aware of, on off. An amplifier means it is a voltage amplifier, an analog domain. So, if I give a smaller peak to peak input voltage, can I get a larger peak to peak input voltage through MOSFETs, right. So, this is a generic sort of structure for this week. Most of you will find you can skip class 1 and 2 if you are not interested in the basics of MOSFET, but you need to attend class number 3 to 5 in a much more rigorous manner. Let me come to the outline for this course. For this class, we will look into typical types of MOSFETs and its operation, maybe a basic equation of MOSFET rather than going into the full derivation of it. We will look into the MOSFET fabrication steps, key terminologies in semiconductor manufacturing, and then finally recapitulate in this lecture slides, right. Why MOSFET fabrication has been introduced? This is the only time possibly in the whole lecture series when a brief introduction of fabrication steps should be, you should know these fabrication steps. And the reason being, when you know these fabrication steps, you know how you can change the process or optimize the process for the best performance of the MOSFET. So, that is the reason these bullets of MOSFET fabrication steps and basic terminologies have been shown to you. For a detailed study, you can refer to many books and many other lecture series which are available online as well as offline. Let me come to a MOSFET now. Till now, we were actually looking at a MOS terminal. When we were discussing, we were looking at MOSFETs, right, as a let me change the color, MOSFET as a two-terminal device, right, and this was dealt in week 1. Now, we look at a three-terminal device for the MOSFET. So, what is a three-terminal device? We will see that first of all. So, we have just now looked into the fact what was two-terminal. Two-terminal was the gate, metal gate, and the substrate. The substrate was grounded, the body or the substrate was grounded, and metal gate you applied a positive bias, remember, and then we were looking into all other aspects of it. Let us look at the first time sort of a in this course the basic cross sectional diagram of a MOSFET, and we will discuss why MOSFET is of 4 types. Look at this point. If you look very carefully, you have to now this was the gate. This black color is basically my gate. This is my gate. This hashed line is the oxide layer, and this whole thing, this blue and all these things, is basically my semiconductor. So that's the reason it's known as a MOS device. But now we have added 2 extra regions here. One is, this is known as the source region, and that's the reason it's shown as source here, and I have a drain region which is N plus region. Now, what does N plus mean? N plus basically means this is basically of high doping, right? So the doping concentration here is relatively very high as compared to substrate. So substrate has got a lower doping, right, which is a p-type substrate, by the way. As I can see, you always apply, if you have a p-type substrate and you want to have an inversion layer, you apply a positive bias on the gate, and therefore you see the bias is basically applied with respect to source always. Please keep this in mind. In most processes, source is generally grounded, right, and therefore when I say VGS, I basically mean it is VG minus VS. Now since VS is grounded, this VGS becomes always equals to VG because VS equals to 0. Similarly, I apply another N plus region which is basically known as the drain region. So now I have got source, right, source, I have got drain, and I have got oxide layer here. I apply a positive bias in case of an N channel p-type substrate bias, and therefore you see this is the positive voltage I am applying here. Now I will explain to you how these terms are, but let me come to the basic idea of the MOSFET first. So I told you MOSFET is generally of 4 types. We can, so depending upon the type of carrier it flows, you can have 2 types of carrier, N type and P type, right. So if N type, it's basically electrons are the carriers of the charge carriers, and if it's P type, it is the holes which are the charge carriers. And then there are again 2 types of structure available. One is known as enhancement mode MOSFET, enhancement mode. So these are the modes of operation, and another is a depletion mode. So I can have therefore N type in enhancement mode and N type in depletion mode. I can have P type in enhancement mode and P type in depletion mode. That gives me 4 types of bulk MOSFETs I can do just by changing the carriers and the type. With this, let me show to you what an enhancement mode is, and this is what is an enhancement mode is all about. Enhancement mode is you are enhancing the charge carriers in the channel by applying a positive bias here. When you apply a positive bias on the gate side, you see your gate current is 0. The gate current is 0 because it is flowing through an oxide layer. You can't have a current through the insulator, and that's the reason a gate current is 0. But surely there will be an electric field. This electric field will do what? Push the holes already below and form a depletion layer. More positive voltage you form, you will form an inversion layer here. And therefore, when you apply a positive bias on the drain side, the electrons are getting pulled towards this side, and as a result what will happen, the conventional current will be in this direction from source to drain. So the electronic current will be from within the device from source to drain, externally from, if you look at the conventional current, it will be from source to drain in the external pulse. So we have learned one thing. Why is it known enhancement? Because you are enhancing the number of charge carriers near the silicon dioxide interface, and therefore this is known as an N channel enhancement mode MOSFET. N channel, why? Because this is basically large number of free electrons are available, right. So it's therefore known as an N channel enhancement mode MOSFET. Let me come to a depletion mode MOSFET and show it to you later on, but before going that, let me go one by one in this case. Let us take up an enhancement mode MOSFET and do one thing, that we go on varying the value of VGS and see what happens. As you go on varying the value of VGS, when you apply a drain voltage, the depletion region on the drain side, this is the depletion region on the drain side, this goes on increasing. Why? Because it is nothing but a reversed biased PN junction diode, right. And as you give the drain bias more and more, the depletion region increases, thereby eating away into the channel, or the channel thickness starts to go on decreasing, and that's what is shown here. You see, The channel thickness is lower as this side as compared to this side. The depletion thickness is larger on the drain side as compared to the source side. Correct? With this knowledge, let's do one thing. Let us plot drain current versus the drain voltage, and drain current versus the gate voltage, and drain current versus the drain voltage here. So as you see, when the gate voltage goes on rising, you see the current goes on rising, which is very obvious, because as the gate voltage becomes larger and larger, you are pulling more and more electron towards the interface, and therefore your drain current starts to increase, and that is what is happening. Correct? This is one thing. The second thing, below a particular gate voltage, the current is approximately equals to 0. Again, the reason is very clear in front of you, because in that gate voltage your inversion layers are not formed. The whole layer is basically depletion. Please compare this with my last lecture of week 1, where I told you that this is the point where the depletion layer thickness will be maximum, and therefore you see, as you increase the gate voltage, the current goes on increasing as you move from top to bottom. At very low values of your drain voltage, it is almost follows the Ohm's law. You see, this ID versus VD follows the Ohm's law, right? So if you take VGS equals to 8 volts, then you see when you keep your drain voltage below about 1 to 2 volts, you effectively have a linear change in the value of ID with respect to VDS. It primarily means it starts to behave like a resistor. So if you bias your device somewhere here or here or here, then it behaves like a resistor. And if you bias your device somewhere here or here, it starts to behave like a current source. And here it starts to behave like a resistor. Correct? Because it follows Ohm's law. And why current source? Because remember, current source definition is that the ideal current source is a one which will give you an output current, varying value of output current, without changing the voltage across the current source. And you see, the voltage is constant and the current is changing as you move along the voltage. Correct? So that's the reason it is a current source, and this is basically a voltage source. Now if you plot this graph on a ID versus VGS graph, then it looks something like this. A parabolic profile will come into picture. Why and how we will not know in good details now, but you will get a parabolic profile where you see, let me rub this portion and show it to you, and I'll show you what do I mean by this. So if you look at this particular point and you extrapolate this one backwards, it cuts somewhere here 3.5, around 3.5. This is defined now as my threshold voltage of the device. Threshold voltage. So after this, you will have appreciably large values of current available with you. Now let's look at ID versus VDF curve MOSFET, the same curve which I told you here, this one, in a much more detailed manner, so that you appreciate the point. If you plot ID versus VDS here, and for various values of VGS, this and this, then you see as the value of threshold. So basically if you look very carefully here, when VGS is just below VTN, or the threshold voltage of the device, you don't have large number of carriers to form the channel, and therefore device is cut off. So I come to the point that when my VGS is less than equal to threshold voltage of the device will be in the off state. Correct? Which is shown here. However, as you increase the VGS from VGS this to VGS this value, which is Vin plus VOV1, and then VTN plus VOV2, and VTN plus VOV3 plus VTN plus VOV4, you see the current starts to rise. Please keep in mind that the increase which you see here, because I will use a better, so the increase you see here and what you see here and what you see here is larger. So as the gate voltage starts to increase, the differential current also starts to rise up. You see, this difference is much larger as compared to this distance, as compared to this distance, and as compared to this distance. So as the gate voltage increases, the value of the current, difference in the value of the current also goes on increasing. Correct? And the reason is to do with the fact that it has to do with basically the number of charge carriers being attracted towards the interface. If you look at the current equation in the saturation, this region is known as the triode region. This region to the left of this region is basically my triode region, and to the right is basically referred to as the saturation region. In the saturation region, we define the current source to be equals to half mu n by 2 mu n C oxide W by L VGS minus VTN whole square, which means that this VGS minus VTN is defined as overdrive voltage, and that's the reason it is known as VOV, where W by L is what? The width divided by length. Where is the width of the device? What is the length of the device? This is the length of the device. This is the length from source to drain under the metal. So this is the drawn length and this is the actual gate length. This is my gate length. This is my gate length. The length below the gate. And where is the width? Width is in the third dimension inside the board, inside your screen, computer screen, right? And you can see it below. So W is this side. Higher the value of W, more will be the current, because more will be the charge carriers, right? And that's the reason you see we define this current to be in saturation to be equals to 1 by 2 mu n C oxide. Mu is defined as the mobility of the charge carriers, right? C ox is oxide capacitance. W by L is also referred to as an aspect ratio, and this is square of the overdrive voltage. What you see is that the increase is not linear. So let us assume that your VGS is say varying from say 4, 5, 6, and your VTN is 1 volt, 1 volt, 1 volt. Then what will be the value? It will be 4 minus 1 is 3 square, 5 minus 1 is 4 square, and this is 6 minus 1 5 square. So this will be 9, this will be 16, and this will be 25. So you see the difference between these two is not equal to the difference which you will have here, right? It will not be equal. It will go on increasing. This gives you a ID versus VDS characteristics of a MOSFET, telling you that on the left hand side of this curve, this is the saturation curve, this is the point where the current starts to saturate, and this is the point where I will get for those values of VDS greater than or equals to VGS minus VTN. For all values of VDS greater than the overdrive voltage, you will always have a saturation. So on the right hand side, which you see is basically saturation region, where if you bias your device, it will work as a current source. Okay, now and if you look at the left hand side, it is where your VDS is less than the overdrive. So on the right hand side, it is VDS is greater than V overdrive, this one, and on the left hand side of this curve, VDS is less than equals to or less than actually your overdrive, V overdrive, and therefore it never behave like current source. And moreover, you will have a non-linearity here in these regions. We will not go into details of that at this stage, but give you an idea about the ID-VD characteristics of a MOS device. So let's look at the point of view from circuit, because we will be coming to that later on. If you want to find out the resistance at this particular point, resistance is voltage by current. Now here, if you see, the current is almost constant. So if you look at del V, del I, then this will be infinity, because del I is 0, and therefore resistance will be infinity, which means that the impedance of a MOS device in the saturation region, output impedance, is infinitely high, right? And if you look at this particular stage, it will have a linear component in the value of your R, correct? So this is also, please keep this in your mind, we will be using it later on in our discussions. Let's come to a depletion mode MOS. So if I have, let's say, a gate, a source and drain, right? And if this is my, let me give you an example. Let me say this, I change it to P plus, and let me change this to P plus. Then even at gate voltage 0, I will have a channel which will be formed between these two regions. And I have to apply a negative gate bias in order to switch it off. This type of devices are known as an N-channel depletion mode MOSFETs. So if you look at the third part here, that the electron inversion layer already exists with 0 gate voltage, and you actually have to also put a negative gate bias in order to remove a channel, or to remove the channel and form a depletion layer there. This is basically my N-channel depletion mode MOSFET, right? We generally, in most of the cases, don't use N-channel depletion mode MOSFET. We are more preferring your enhancement mode MOSFET. Okay, just to move ahead and just to give you an idea about the structure or the schematic of an N channel and P channel. So there are two ways in which people refer to. One is this, right, Another way of doing it is we don't name it and we say we put a bubble here. This bubbling is basically a PMOS. If you don't put a bubble, then it is basically an NMOS. Another way of doing it is look at the arrowhead. If the arrowhead is away from the device, right, then this is basically your N channel. If this is source, drain and gate, this is again drain, gate and source, drain, gate and source. And if you have the channel, the source, something like this, gate, drain and source, then we define this to be as a P type. Why? The direction of the arrow gives you the direction of the conventional current. So, in a P type semiconductor, the channel is basically made up of holes, and when you apply a negative bias on the drain side, the holes are pulled towards the drain side, and therefore the conventional current flows from source to drain, and that is the reason the direction of the arrowhead is in this manner. Whereas in an N channel MOSFET, when you apply a positive drain bias, you are pulling the electrons, which basically meaning that the conventional current is flowing from drain to source, and that is the reason the arrowhead is pointing away from the source region, right. And this is so many places in many of the books you will find either this notation or this. So, there are two types of notation. There are other notations also, but as far as we are concerned, we will be following either of these two notations, preferably this one to a larger extent. At this stage, we don't want to I don't want to show you for depletion what is the overall how it looks like. For enhancement, how does it look like, but we are very much sure that at this stage in depletion, we already the charge carriers are present. I require to give a voltage to have a depletion region and cutoff, whereas in enhancement mode charge carriers are not present. I have to give a gate voltage to form the charge carriers known as the threshold voltage. Here also in N channel depletion mode MOSFET, the negative gate voltage which I give in case of a electron, in case of a P type semiconductor, is basically defined as my threshold voltage. So, if this is P plus P, positive gate voltage here, correct, to push all the holes on this side. This is if you put a negative gate, this I already discussed with you, but nonetheless. So, in the same graph I am showing a positive gate and negative gate bias. You see, when the gate bias is more and more negative, the current starts to fall down. Why? Because if you have a P type substrate, as you make the negative gate voltage go higher and higher, you're basically pulling the holes towards it, due to which the recombination process takes place and the current starts to fall down, right. Whereas if you look at ID versus VG, you will see that somewhere on the left hand side you will depletion mode, on the right hand side when the gate voltage is positive you will have enhancement mode for at least a P type substrate and N channel being formed, right. And this is the reason on the same graph we are able to draw both depletion mode and the enhancement mode MOSFET. This is the P channel enhancement mode and this is the P channel depletion mode on the right hand side, right. I have an N type layer and I have shown to you, and already this is given to you as such. There will be small change here, there is a small mistake here. When this is in depletion mode MOSFET, this should be P actually, right, this will be P, and when this is P, you already have a channel being formed here. You apply negative gate voltage here, a positive gate voltage here to push the holes back inside it to form the depletion layer. Now, let me quickly take up the basic fabrication steps which are available for a MOS device. The first is basically we use a photoresist, alright, and then we prepare the silicon wafer, and this preparation is by itself a very tedious process. Not many fabrication houses have these wafer preparation being done, very few of them have it. And then we do a photoresisting, then we go for you do a lithography here, projected light, then this is where a reticle or mask is there, and from this mask you throw a light wherever the light passes through those regions where the mask is clear, and it falls through this lens onto the silicon wafer, and this is where the patterns are generated, right, using photoresist. The exposed photoresist are removed. Is exactly the same as we do using camera, the old cameras we used to do, right, and that is how you do it. This is then what you do is that all the exposed photoresists are etched out or removed, and you are left with this one, and then those areas which are unprotected by photoresist, we etch it by gases or chemical. Then we start doping using external ion sources, and then we do final connection of the metal at the top layer, and that makes the fabrication process clean, and overall gives me a good process step. Let's look at the basic terminologies which we will be using in semiconductor manufacturing. The first step is of course the photolithography, and this is the process of transferring pattern on the mask to the photoresist layer. So I have a mask, and that is basically the IP of the fabrication house. The mask will have thin patterns being generated. Now when you put a light across it, it will pass through those pattern, and it will try to expose the photoresist which is there in the on which has been landed onto the silicon wafer. Once it exposes it, it tries to materialize it, and then you can use a chemical etching to remove those parts. And that is what the second point is all about. It is the process of permanently removing the unwanted part of the design on the wafer surface to get the desired pattern. Remove the unwanted part, right? And we don't want that part to be part of the silicon wafer anymore, and that is known as etching. Now you need to form a dopant layer, right? Because as you can see, for example, in a MOSFET just now which we have seen, I require a source and drain where the dopant species are relatively high concentration. This can be done using a diffusion process. How do you do diffusion? Diffusion is basically transfer of molecules from a region of high concentration to a region of low concentration, right? And we do it at variable temperature, typically at high temperature, and by modifying the temperature and the concentration gradient, I can have a very large diffusion being done or a very small diffusion being done. Now this is the third process which we do. The fourth process is you want to do ion implantation, right? For example, you want to bombard high energetic dopant species in a high electric field chamber, so that the dopant species are able to sit at an appropriate position within the wafer or within the system, so that you are able to have an appropriate number of charge carriers available. Next process step is oxidation, where you need to grow a thin or a thick silicon dioxide layer where you want to use it. So if you want to use a oxide layer at the back of the device, we define that to be as a box or a buried oxide. There the growth of the layer will be very thick, whereas if you want to grow just below the metal, it will be quite thin. And you can actually change the rate of oxidation by either using a water vapor or using a high temperature or low temperature. Many wafer processes also do a CMP, which is basically chemical and mechanical polishing, and this is process to physically grind the flat surfaces, right, to have planar surfaces. And the reason we want to have a planar surface is to have a better exposure at photo process. So when you do a photoresist design and photo processes, if your surface is not planar and if it's very uneven, then you will have very difficulty in removing the photoresist, and therefore CMP is quite an important process which you do. These are the few steps which I have discussed with you. So let me recapitulate what we did till now. We did obviously the 4 types of MOSFETs I explained to you, types of MOSFET, right? And these are what you have an N channel or P channel, and within N channel you can have enhancement mode, or you can have a depletion mode. Same thing happens for P channel, enhancement and depletion. For an N channel enhancement, the threshold voltage is always positive, whereas threshold voltage is always negative in case of a N channel. P channel enhancement, the threshold voltage is always negative, whereas for depletion mode, threshold voltage is always positive. I leave as an exercise to you to just verify this from any standard look. Further, we have also seen how does the current behave in a saturated state and in the non-saturated state, and we saw this to be equals to mu n C oxide aspect ratio W by L into Vg S minus Vt H whole square, right, and gives me an idea about how the current will flow in a MOS device as a current source. Understood the concept of threshold voltage both from the point of view of a 2-terminal device as well as from the 3-terminal device. So we understood therefore 1, we understood 2, we understood threshold voltage, right, and the implication of threshold voltage onto the device characteristics, right. And finally we looked into the process steps. I kept it very minimal here, process steps, very minimal in description, because we won't be using too much amount of process steps, at least for this coursework. So, I have given you a brief idea. You can have a look into other books and other resources for the case of fabrication. With this, we come to the end of this lecture. Thank you very much.